Thanks for joining. Welcome to this session. I'm going to be talking about the impact of micro-optimizations on large-scale applications. So first, a little bit about me. My name is Damian. I'm currently a software engineer at Meta. I work at WhatsApp. And I think by now I probably have over 15 years of experience in software, working in all sorts of tech stacks. Started with good old PHP and moved to backend data, and then ended up with mobile apps somehow. And right now I'm kind of doing full stack, so pretty much whatever is needed to be done. Yeah, that's me. A bit about the presentation or the agenda. So first, we're going to look at optimizations in general, meaning what are optimizations, what kind of optimizations do we have. Then we're going to look a bit closer into resource optimizations. And from there, we'll move towards the benefits of micro optimizations and, very important, how to measure them. After that, we're going to look at a few case studies of large-scale applications that implemented micro optimizations. These will be, I want to say, a bit turned into generic examples. So they should be applicable to more, like they're not very specific to a certain app or like a tech stack. So it's more generic. And after that, we're going to look at some best practices. All right, let's get started. So the first question, what are actually optimizations? Optimizations are techniques used to improve performance, efficiency, scalability or reliability of your application. In the context of a mobile application, that means we try to minimize the usage of system resources while maintaining or improving the user experience. If we take a closer look at resources and resource optimizations, the first thing we have to do is we have to acknowledge that building mobile apps can be quite complex. Mobile devices or mobile apps are working on very constrained systems. The phones are getting smaller. Okay, some of them are getting larger. They're kind of turning into phablets, but still they are very constrained and they have a lot of computational power. But the systems that we are building are also getting more and more complicated, and the devices have more and more capabilities as well. They are getting higher resolution, higher frame rates. I don't know where we are right now, 120 hertz or something around that ballpark. So lots of frames to be drawn. More and more connectivity. We have now 5G, NFC, everything in one tiny modem. And they also get more and more sensors. So if we want to optimize our systems for resources, there's a couple of ways that we can approach this, right? We can, for example, only request data that is required in that specific part of the app to render information. We keep data in like a local cache or database to avoid requesting it again. We can downscale resources and bitmaps that we are downloading or requesting to reduce the memory footprints. And we can optimize computations and choose more efficient algorithms. We can also defer computations and prioritize the urgent work, so the one that is kind of latency sensitive, that needs to be done right now to show the user progress in the application. These optimizations would make our app more performant, more reliable, more efficient. And there's a couple of quotes that I added about some of the typical issues that we have if we don't optimize our application enough. I think we are pretty much familiar with those, but ANRs, so app not responding, meaning if the main thread is blocked, there's like 60% of one-star reviews mention app crashes or freezes, and a lot of them can be traced back to ANRs. Then there's the user experience that we can also improve with these optimizations. There's this data point that a 1 second delay in loading time can lead to a 7% reduction in conversions. And the next one is about competition. That kind of summarized the whole topic, right? So if you build a more reliable and a nicer application, then the users will be happy about that as well, because there are millions of apps or hundreds of millions of apps. For every single use case, there's like 3, 5, 10 applications that do exactly the same. And if ours crashes, then the users are probably going to churn and just go somewhere else. So circling back to the optimizations itself, there's a couple of types of optimizations. The first one that we're going to look at is macro optimizations. We will look at the micro optimizations in a little bit. So if we try to figure out what the macro optimizations are, these are usually high-level system design decisions that impact the architecture, the functionality. For example, choosing the right data structure, the right algorithms, or an efficient database schema, or good caching mechanisms throughout the application. So these are generally larger decisions that impact the global data structure, the global application structure, and system design and flow. The micro optimizations, on the other hand, they are more small-scale improvements. So we are focusing on a very specific part of the code or of the system. A couple of examples would be, I know a lot of people don't like it, but using bitwise operations instead of arithmetic operations, or minimizing object allocations and garbage collections, or optimizing graphics rendering. So these could be more low-level optimizations compared to the high-level one, the macro ones. And the question is, why do these actually matter? So if we look at them individually, they might not have the largest impact, but the impact grows significantly when they are combined and applied consistently throughout the code base, especially in scenarios where, for example, every millisecond counts. So if we have to do real-time processing of data, or the battery life is critical, let's look at wearables and like even smaller devices that we are building apps for. Or if the resources are severely limited, this could be just low-end hardware, or in markets where the network connectivity is not as good as, for example, here in Germany, right? So if that is all very much constrained, then these micro optimizations will become more important. There's also a couple of challenges that come with the micro optimizations. So the first one is it's difficult to measure the impact. They may not be noticeable in isolation. So it's kind of hard to test them locally, for example, on an emulator, because there are too many variables in execution. The emulator will always behave a bit differently because it's in the end an emulator. And even the devices that we have as test devices, there's just too many variables at play. The next one is that the benefits may appear in different parts of the app. So we could be doing an optimization in one part of the application, and we could see benefits in a completely separate part of the application. If we keep for example, the memory pressure low, and we end up with less garbage collection, then we end up with less out-of-memory errors. But these usually don't happen at the exact point where you're doing the optimizations. They would happen at a later time and point when the user's, for example, using a different part of the application. And then they also bring a maintenance overhead. So if you look at there's a lot of these competitions, right, where people write like the most concise piece of code. And in the end, heavily optimized code will be more complex and harder to understand. It is a challenge in itself to maintain this code and to debug it. And the example I mentioned earlier, right, moving from arithmetic operations to binary operators, it is just harder to read for most of us, at least for me. So the thing is that optimizing code doesn't have to mean it should be short and unreadable or harder to maintain, because our compilers are very smart, right? They will do a lot of that work for us, and they will do a lot of optimizations as well before we actually ship the application. So while these micro optimizations can be challenging, there's also a lot of benefits that they bring. For example, the cumulative impact. If we apply them consistently through the application and we just make sure that we work on the ones that we identify, they will add up and in the end make a significant difference. We will get reduced latency since we will be optimizing mostly the critical code path in our application, and we will get better battery life. It's always nice if the phone doesn't die that fast. So minimizing the power consumption, that will just extend the battery life as well. And there's many more. So if we look at large-scale applications, the picture will shift a little bit. If you imagine the app that you're working on, that it's used by billions of people around the world, so you have a presence in pretty much every single country on the planet, then these micro-optimizations will not just improve the user experience, but they can actually enable access to a certain to a certain market or to certain people with certain devices. These optimizations, they will specifically also apply to older devices and low-end hardware with more limited resources. And in the end, this is going to increase the reach of your application. In the end, this is going to lead to increased adoption, especially in, for example, emerging markets. And in markets where people have high-end devices, these optimizations may not be as noticeable. But just as I said, in the low-end devices, they will make a very large difference. To actually prove that our optimizations make an impact, we need to be able to measure them. So we're going to do a quick detour into measuring the performance. So there's a couple of metrics that we can look at. For example, load time reduction, which usually leads to increased user engagement and retention because people are just happy that they can use the app faster. There's a battery life extension. This can lead to increased daily actives and improved satisfaction. If the phone doesn't die as fast, like in the end, people can also use our app more, right? And then there are data savings. This can translate to cost savings for the user, but also for the company itself or for you, because in the end, people are going to request less data, which someone has to pay for the traffic. And this also leads to an improved performance and can lead to more or higher usage of core features of the application for users with, for example, limited data plans. So a couple of common metrics that we can use to evaluate the effectiveness are, for example, the execution time, meaning the time it takes to execute a certain path of code. Then CPU usage, for example, how many threads are active at a given time, how much work is being done, and how long does it take until our work is actually being run or prioritized. Then the memory allocation, just to see how much memory pressure there is on the device, and the power consumption. So we can measure how much energy is consumed by the application itself. So if we dive a bit into the measurement of execution time, to collect the data in a simple way, all we need to do is record the timestamp of start and end. So we can do that on a test device, or we can do that in a production environment. While the test devices are going to give us initial insights into the performance, the measurements in production will always give us more reliable information and more reliable data. So here we have to keep in mind that measuring in production will always also have an impact on the performance itself. So we can't just measure performance for every single user, because in the end, just tracking all of this, like tracking the timestamps, even if it's just a timestamp, it will still have an impact on the app performance itself. So we should sample the data collection and execute it on a subset of devices and only do it for the parts that are critical. So in a very simplified way, what I just mentioned, we would just be saving timestamps, right? We would save one right before we perform the code that we want to measure, and then a timestamp after we successfully executed that code path. And then we're just going to calculate the delta, and that's going to be our time to execute this code path. So in the example, we're not using any specific framework or specific class, because all of that is going to be very much dependent on your system, on your application, on your code base. So these examples will be very abstract from that, very generic. So if we look at real life scenarios, usually things become a bit more complex, right? We don't just have one function that we need to track. Instead, we have a path. We have, for example, multiple functions that we would like to measure the performance of. In the example here, there's a multi-step flow that saves a message to a local database. Then it's setting the message up to be sent to the server, and then also updating the view state accordingly. And the way that it's set up right now in the example, we would get the execution time for the overall code path, and that's going to give us good insights as well. We are going to know, like, how is the overall performance of the system, of this whole flow, but we're not going to know much about the individual sections. So if we see an increase in execution time in our dashboards and our monitoring, we would know that it's there, but we wouldn't really know where exactly it is. So to get more fine-grained data and information, we can work a little bit on how we measure this. So the performance logger that is used in the example here is also just an interface in the end. So it's also specific to your project. So it doesn't matter too much. We're just starting a trace at the beginning of the section, and we are adding some points during the execution of our code path. And this more fine-grained data is going to allow us to check which part of the multi-step flow is going to be a bottleneck and how improvements are going to impact the overall performance. So once we have collected these metrics, we have to figure out a way how to analyze them. So an essential part of performance optimization is to monitor the metrics continuously to make sure that we catch bottlenecks and regressions early and can fix them. So usually we would look at trends and patterns in the data. We would identify outliers and anomalies and compare the metrics across different scenarios. There could be certain device types or network conditions that impact the overall performance. And we don't want our users to be stuck in a certain flow just because of low connectivity. So this would help us identify these bottlenecks. We also don't want specific device types to have issues. If it's a foldable, a flippable, or any of the new device types. So we can use these metrics also to figure out where exactly on what kind of devices does it happen. We're going to use statistical methods to summarize and visualize the data, and then turn them into graphs, set up thresholds, set up alerts. That kind of depends on the data pipeline that is available. When analyzing the metrics, we would be looking for the bottlenecks and insights into critical user paths. So a high execution time could indicate a bottleneck for the code path. And the questions that come up are, can we make it faster by optimizing? Can we move it to an async operation? Can we break it into smaller parts and maybe defer the long-standing operation for later to give the user faster feedback? If we look at the standard deviation of the data that we are collecting, this could indicate a variability in execution time that will be harder to optimize. So we will need to dive in a bit deeper to understand the variability, and we need to add more fine-grained monitoring until we have pretty much the whole flow figured out and we can narrow down where the bottleneck is from. So once we have the data, we can look for correlations between metrics, such as execution time and CPU usage, to identify the potential causes of the bottlenecks. These performance metrics will most often also impact product metrics. So we have to make sure to also check product dashboards for the impact of our optimizations. The easiest catch would be a high crash rate is going to reduce product metrics because people just can't use our app. But there's also a lot of different ones. So if we have a high execution time, it will also reduce the number of actions the user may perform. So if we make our app faster or just more responsive, then users are able to do things more often or to do them more reliably. So in global scale applications, the distribution of metrics will also provide valuable insights. By comparing the 50th percentile and the 95th percentile, we can understand the spread of execution time. A large gap could indicate a bottleneck that affects a small percentage of users, but with a very significant impact on performance. So this could even render certain parts of the app, in the worst case scenario, useless for certain users. If the app is freezing, the users are stuck, or the app is just crashing. So based on the analysis, we can identify optimization strategies. If we focus on the worst case scenario, we will ensure that the majority of users will experience a good performance. If we optimize for the average case, we would optimize for the overall performance. But here we have to be mindful. We can use techniques like caching, parallelization, lazy loading, deferring to reduce the execution time. And we can reduce the amount of in-memory data to reduce memory pressure. But we can also ensure that the app works well in low bandwidth scenarios to make sure it's accessible. So to validate the effectiveness, we would be using A/B tests and experimentation, meaning we will have multiple versions of the code in our application, each with different optimizations. And we can test each of those variants on a subset of users. Then for each of those experiments, we would use the statistical methods that our tooling offers or that we run in the company to ensure that the results are significant. That means we have enough users exposed in our experiment, and we also have enough data collected. If our user set is quite small, then there will still be a lot of variability in the data. So the too long didn't listen version of this part is optimization is an ongoing process. It requires continuous monitoring, continuous improvement. We should set up a dashboard to track the key metrics, not just product metrics, but also performance metrics. Use alerts and notifications to detect changes in these parts, and regularly review and analyze metrics, and then continuously iterate. Look at the code, try to find more optimizations, try to find ways to improve it. We're going to look at a couple of case studies, a couple of real-world examples. So for these, I won't be going too much into product details, so the examples will be a bit more generic, but I'm pretty sure that they will be in a lot of applications that are out in the world. So the first example is a quite straightforward one. It's a parallelization of asset downloads. So we are just moving from sequential download to parallel. It has a couple of effects. The primary effect is we would have a better utilization of the device capabilities. We would have faster rendering. But there's also a secondary effect, which is we will have a higher active thread count, and this can lead to increased stress on low-end devices. So for things like this, we still have to put in guardrails and use, for example, limited parallelism and monitor how this works also on different sets of devices with different capabilities. So based on the capabilities, we would be using more or less parallelization, and maybe in some scenarios, we would completely turn off the parallelization just to make sure that the app still works also across all of our feature sets. The next example is about layout improvements. So that's an example that I personally like. It feels a bit counterintuitive, but in this example we would be moving from a grid layout to a linear layout, and we would start to manage the subviews on our own. This was in a quite high volume surface that I was working on some time ago. And I spent some time looking at optimizations, how to improve the performance of that part. I will have some visualizations on the next slide, but just an introduction. So the grid itself will have more individual cell items that are part of the pool that is used to render and to populate the data. And switching this to a vertical layout will have less views that are managed in this structure, but the views will be more complex. So the primary effect of improving this part would be improved scroll performance, for example, because it should be easier to render the new views that are coming up. But the secondary effect would be that the view inflation time is also increased, because the views are more complex. They are now hosting more items, so it takes a bit longer to inflate them. So guardrails for this one would be, we still need to keep the hierarchy as flat as possible and offload the binding to a background thread and do as many parts as we can on background threads in general in terms of data. So this is the before view. It's a grid with individual cell items. And in the actual example, it was about 8 items per row, but my drawing skills are not good enough to visualize that properly. So here it's just 5. This is kind of depending on the device screen size. And we noticed that with the performance monitoring that we added, that there was poor scroll performance on specifically low-end devices under certain conditions. So we looked a lot into what can be improved, what could be the root cause of this. And after a bit of experimentation and refactoring, we ended up with a slightly different layout that feels a bit counterintuitive. But in this case, it actually improved it. So we moved away from a grid. We moved to, let's say, like a linear layout. It's just a vertical layout where each row is exactly 1 item. And each row is also a horizontal list of items with a predefined amount of items, of views in there. So this kind of reduced the amount of views that need to be reused and recycled, because now each view so it's just one row and it's not 5 per row. And this improved the scroll performance quite a lot. There was a very large reduction in frame drops that was noticeable. And in the end, this also led to an increase in engagement, especially on low-end devices. So the TLDR is, it always makes sense to analyze the layout hierarchy. Doesn't matter what kind of layout system you're using, it always makes sense to analyze this for high volume or very frequently used parts of the app. Diving in deep here to figure out where the bottlenecks are makes sense. And this will always be highly dependent on the implementation, on the use case, on the data that you're displaying. So in this case, we also made some changes to the data pipeline, batching the items into smaller groups before sending them to the UI. So this could also be part of the reason why the whole system is now working faster, because it has reduced the overall work on the main thread. And in the end, it worked out quite well. So it felt very counterintuitive at the beginning, but that's life sometimes. The next example is a very small one, a short one. It's about view stubs. View stubs are used to extract views out of layouts. And these stubs are just going to be an empty view until they are actively inflated or rendered on demand. As an example, we often have a separate experience for new users where we want to introduce them to our UI, to our app, to a specific feature or to changes to educate them. And these experiences will be conditionally rendered. So we have to make sure that we don't include them in our layout by default, since they would not be rendered in most of the cases. So if we look at an example, this is Android views, XML. I know not everybody likes it, but that's life. I've shortened the syntax quite a bit to make it fit onto the screen. Otherwise, it would be more than one slide. In the example here, we have a bunch of text views that are kind of stacked on top of each other. There's a button, there are 2 recycler views, and then there's a linear layout that also hosts a bunch of views. And this linear layout on the bottom, it contains the new user experience in this case. So it's a few images, it's a bit of text, and then a button to maybe just dismiss it. And this part is only going to be shown to users that experience this part of the product for the first time. So if we keep it like this in our hierarchy, in our view, then it's always going to be inflated. It's always going to be rendered. There's always going to be a bit of memory impact, even if we set the visibility to gone or try to hide it. It will just not be measured, so the impact is not going to be as large, but it's still going to be there. So if we replace the whole linear layout on the bottom with a view stub, then the layout looks a lot cleaner as well. The view stub is going to be inflated on demand. So whenever we notice that it's actually a new user, that's when we're going to be inflating this view and displaying it. This has a few advantages, but also some disadvantages. Since the view stub is going to be inflated during runtime, so for example, whenever a user clicks on a button or performs a gesture, this can slow down this specific path for users who would see the conditional experience. For a simple view, for just a text or an image, this might be too much complexity to extract into a view stub, so it may not be worth a change. But for more complex layouts, it will make quite a large difference. In a similar setup as the one shown previously, I worked on replacing part of the layout with a view stub, and the reduction of inflation time that I noticed was actually around 50%. 50% is quite a lot, especially again if you look at this also in the together with low-end devices where the inflation time is really often a very high blocker for things. And if we get these improvements into high-volume surfaces, then that most users are going to use and are aware of, it will bring us a lot of benefits. So, yeah. The next one is about application context. So application context is kind of like this omnipresent thing in an Android app. And the example here feels a bit more hidden. So we use application context sometimes in the app. We use it, it provides references to some of the global state, and it can give us access to system services or, for example, cache directories or in general, a lot of directories that we might use. If the application context is used in too many places, we can end up with random locks on the main thread, especially if the context is also accessed on background threads. These threads can end up creating ANRs in the end. So if we look at the implementation of application context, we will see that a lot of these functions are synchronized. They're using the msync lock when accessing, for example, cache directories or file directories, like in the image that I added here. So this is done that to ensure that the object is actually initialized and accessible. But after initialization, the subsequent calls are still going to be synchronized. They will still use the same lock. And the same lock is used for a bunch of these. So here's a quick overview of a couple of these files. For example, cache directory, database directory, and a bunch more that are all locked with or guarded by the same lock. So if we are in a scenario where we have multiple threads and we are trying to access some of these directories in our multi-threaded system, then we might end up locking our threads until this has been done. And this can lead to ANRs or crashes, and they will be very hard to debug, and they will be very hard to fix or find the root cause because they are quite deep down in the infra part. So to recap this part, it's good to be cautious about accessing the application context in general, especially in multi-threaded environments. Use caching for things like file objects that point towards cache directories to avoid triggering this synchronization too often. All of this mostly applies in multi-threaded environments, but most of applications are multi-threaded, so it pretty much applies to most of the applications. So if we look at now that we looked at a couple of cases, if we step back a bit and we look at best practices, the first one would be focus on critical code paths and bottlenecks in your application. Then use metrics, use profiling tools to guide the optimization efforts. So it makes a lot more sense to start monitoring performance first and then optimizing, so you actually know that it did something. Implement the optimizations incrementally, measure their impact, and consider trade-offs between optimization and maintainability. And then the last one is continuously monitor and refine optimizations over time, because the system will always change. Depending on how many people are working on the same code base, there will be a lot of changes in a lot of different places that can all impact each other in some way or another. They can all impact memory pressure, things like that, active thread count. So it's good to keep an eye on this and do it continuously. So in conclusion, these micro optimizations, they will have a significant impact on performance, on efficiency, especially in large scale applications where you are kind of everywhere, but in the end in all applications. And by understanding how to measure and analyze these metrics, we can identify opportunities for optimization. And by applying the best practices and optimization strategies, we can then improve the performance, the efficiency, and the reliability of applications. And the last part, I'm saying it again because it's very important, continuous monitoring, continuous refinement. These are the keys to ensure that the optimizations actually stay effective over time. That's all I got. Thanks for listening. And if you have any questions, I'll be around.